graphed a few polar equations, but today I want to focus on one type of polar equations called limacons and the graphs for those. Now a limason takes on the form r is equal to a plus or minus b times the cosine of theta, where a and b are real numbers. Or it could be a plus b sine theta, or a minus b sine theta. So anything that takes on that form is going to give us a graph which we call a limason. So let's jump right into an example. I want to graph r equals 3 plus 2 sine theta. Now, first, let me make sure that we're all on the same page here. In rectangular, we had ordered pairs x comma y. And we usually had equations y equals something, like y equals 5x minus 1. And then we made a t-table. We labeled our columns x and y, just like our ordered pair. And then we picked a value for x, plugged it into the equation for x, and solved for y. And then we picked another value for x and plugged it in, etc. And then we plotted all those points. In polar, our ordered pairs are r comma theta. So we're still going to make a t-table, and we're going to label it r and theta instead of x and y. But instead of picking a value for r and plugging into the equation and solving for theta, most of our polar equations are going to be r equals. So it's going to be easier to plug in a value for theta, evaluate it, and then figure out what r is going to equal. Okay, so that's kind of a little bit backwards in terms of which variable we're going to pick a value for and then evaluating the other based on our equation. So I want to make sure that's clear. Okay, so now let's go ahead and try and graph this. So we're going to make a t-table. We're going to label it r and theta. And now let's pick an angle. So we might as well start at 0. Seems logical. And then let's get an arrow here to help us out. If I take 0 and plug it in here, what's the sine of 0? That's 0 times 2 is 0. 3 plus 0 is 3. Whoa, my arrow shot off the screen. That's how excited it is. All right, so now we want to pick another angle. Well, I'll tell you what. You can either do all the ordered pairs and then plot them, or you can plot them as you go. So let's see, at 0 radians, r is equal to 3. So let me plot that point way over there. All right, let's figure out another angle. So I guess pi over 6 would make sense. And then we figure, hey, what's the sine of pi over 6? I forgot, where's my unit circle? That's why we had to memorize it. Sine of pi over 6 is a half, times 2 is 1. 3 plus 1 equals 4. So at pi over 6, we're going to get r is equal to 4. That's way over here. All right, let's pick another one. How about pi over 4? Uh-oh. What's the sine of pi over 4? Oh, that's not a nice number. That's square root of 2 over 2. 2's cancel, so we get 3 plus the square root of 2. How do I graph that? Well, everybody knows that the square root of 2 is about 1.4. So that's going to give us approximately 4.4. So I guess I could graph that. Where is that? That's, how about right about here-ish? Okay. You'll see some people will want to avoid some of the angles based on which function we're using. So if it's a sine, pi over 6 is good because the sine is a half. But here and here, we get square root numbers, and it's going to be hard to figure out our answer for r. So, but I'll do it for the first quadrant just to make sure we understand what's going on. Obviously, the more points we plot, the better our curve will look. So what if we picked pi over 3? Well, then we're going to get r is equal to 3 plus 2 times the square root of 3 over 2, and the 2's cancel. We get 3 plus root 3. And then we're in the same dilemma. What's the square root of 3? I don't know. Oh yeah, it's about 1.7. So we're going to get about 4.7 for the r. And I'm going to have to eyeball that one as well. So how about, I don't know. Does that look good? Looks good to me. All right, now we get to pi over 2, and finally we get an easy one. What's the sine of pi over 2? That's 1. Times 2 is 2. 3 plus 2, 5. Well, I can plot that one. That's way up at the top. So you can see what's happening here. I'm going to connect these. So we have the r values are getting bigger, and we got this nice curve going up like that. And like I said, the more points you plot, the better it's going to be. But I'm not going to go through and plot all these values. Now, I could say, well, hey, how about 2 pi over 3? There's really nothing I need to do for that because I know it's going to be 4.7. How do I know that? Because I'm clairvoyant. No. Because I remember when we were doing the unit circle that when I start at 0, the cosine is 1 and the sine is 0. But as I start moving up, the sine is getting bigger. And as I get to pi over 2, the sine is 1. And then in the second quadrant, the sine is getting smaller again, and eventually back to 0 when I get to pi. So the cosine values get smaller and become negative in the second quadrant. But in the first and second quadrant, my sine values have some symmetry, don't they? At pi over 6, I get a half, which is the same as 5 pi over 6. And at pi over 4, I get the same value as 3 pi over 4. And pi over 3, I get the same as 2 pi over 3. So when I'm making my table of values here to try and graph this limacon, because of the symmetry that I understand that goes on with the sine function in the first and second quadrant, this will be really easy. So I can do 3 pi over 4 is going to be the same as pi over 4, or about 4.4. And then when I get to 5 pi over 6, that should be the same as it was at pi over 6, and I should get 4. Now, I mean, you can keep plugging these values in each time and evaluating, but you'll save yourself a lot of time when you realize the symmetry. So let me go ahead and plot those points. So I'm going to have over here is about 4.7, and then here it's about 4.4, and then at 5 pi over 6 it's 4. And then what happens when I get all the way down to pi? Well, the sine of pi is 0, so I'm going to get r is equal to 3. 1, 2, 3. So you can see that the graph looks pretty much the same in the second quadrant as it did in the first quadrant, just reflected over. I know it's not a y-axis, but if you think of the y-axis there, you have that y-axis symmetry. All right, let's keep going. Let's get rid of those so I have more room. And let me redo my table. So we had pi over 2, and we got 5, and we had 5 pi over 6, and we had 4, and then at pi we had 3. Okay, let's go to 7 pi over 6. Now, what happens to the sine values? Back to this graph. At 7 pi over 6, now, after we get past pi, now the sine values are negative, more negative, more negative, most negative at 3 pi over 2, less negative, less negative, less negative, and 0. So between pi and 2 pi, my sine values are all negative, getting the most negative at 3 pi over 2, and then getting closer to 0 as I get closer to 2 pi. So that means if I figure out the sine values in the third quadrant, they're going to match the ones over here in the fourth quadrant. And that'll help me a lot when I'm plotting points in my table. And so I can save myself a little bit of work. Okay, so at 7 pi over 6, the sine is negative 1/2, times 2 is negative 1. 3 plus negative 1, that's only 2. And then I'm going to jump to 3 pi over 2. And at 3 pi over 2, what's the sine? Negative 1 times 2 is negative 2. 3 plus negative 2 gives us a 1. That's going to be our smallest r value in our whole entire table, because that's the smallest value we can get for sine, and that happens at 3 pi over 2. All right, and then at 11 pi over 6, that should match the 7 pi over 6, so we're going to get 2. If you don't believe me, plug it in. And then at 2 pi, sine is 0 again, and we're going to get 3. And then once we're done, after 2 pi, we don't have to keep going, because now we're going to be right back here, and we're going to start all over again and get the same values. So it won't be like the spiral of Archimedes, where we just kept picking bigger and bigger angles, and the r values kept getting bigger, and that went on forever, ad infinitum. We can stop at 2 pi for this graph, and we know that that'll be the complete graph. So let's see, I need to plot some more points. 7 pi over 6, we had a 2. At 3 pi over 2, we had a 1. And then at 11 pi over 6, we were back at 2 again. So r was getting smaller and smaller and smaller, and then starting getting bigger and bigger, and then just keeps repeating. And there you go, you've graphed your first limacon. Very exciting. Or maybe you watched me graph my 57th limacon, or so on. All right, so let's try another one, except this time hit pause, try it on your own, and then go ahead and hit play and see how you did. All right, I'm going to do this one a little more quickly because you should have the idea now. So I make my t-table with r and theta, and then I'm going to pick some angles. I'm still dealing with the sine function, so I'm going to pick angles that make my life easier, like pi over 6, and pi over 2, and 5 pi over 6, and 78 pi over 95, and wait, now just making sure you're paying attention. 7 pi over 6, 3 pi over 2, maybe an 11 pi over 6, and then 2 pi. And then we realize that it's just going to keep repeating. All right, so I'm going to plug in, so I'm going to take each of these angles. My arrow doesn't want to be alone. I'm going to take each of these angles, and I'm going to go ahead and plug them into the equation here for theta and evaluate for r. So, like I said, I'll do this a little more quickly. Sine of 0 is 0, times 3 is 0, 1 plus 0 is 1. Pi over 6, I'm going to get a half. So 3 times a half is 3 halves, or 1.5, plus 1 is 2.5. At pi over 2, I get 1, so 3 times 1 is 3, 1 plus 3 is 4. So r is getting bigger. At 5 pi over 6, I'm only going to get a half times 3. 3 halves plus 1, I get a 2.5. And at pi, I get sine is 0, so r is equal to 1 again. Now, at 7 pi over 6, the sine is negative a half, times 3 is negative 3 halves, or negative 1.5. 1 plus negative 1.5 gives me a negative 0.5. Uh-oh. What is that going to mean? Remember how we graphed negative r's for a given angle? So we're going to do that in a minute. Let's try 3 pi over 2. So sine of 3 pi over 2, negative 1, times 3 is negative 3. 1 plus negative 3, a negative 2. 11 pi over 6, I'll get negative 0.5 again. And then at 2 pi, I'll get the same answer that I got when I was at 0, and that's 1. All right, so let's plot these. I didn't like that. Fix it. Better. Let's plot these points, see what we get. So at 0 radians, r is 1, right there. At pi over 6, we're going to go 2.5, huh? So right about there. I didn't do the decimals for pi over 4, pi over 3. Pi over 2, though, I have 4. 1, 2, 3, 4 circles out. That's assuming that all my circles are 1 units. We could change that scale if we needed to, based on our table. 5 pi over 6, 2.5. So back to here. And then at pi, we're only at 1. Got it. All right, so let's draw this so far. So far, I've got this curve. It's coming out here. R is getting bigger. And then R is getting smaller. And I'm there. Okay? And if I pick more points, it would probably be a little more accurate. Now, it gets interesting. So now, at pi, when I plugged in pi, I got r equals 1. When I plugged in 7 pi over 6, I got r equals negative a half. So that means that somewhere between pi and 7 pi over 6, when I plug that angle into here, I'm going to wind up getting r equals 0. So somewhere after pi, before 7 pi over 6, my r's are getting smaller, smaller, smaller. They'll be 0. And then at 7 pi over 6, I get a negative a half. So instead of coming out half a unit this way, I'm going to go half a unit that way. So let's go ahead and try and roughly plot that. So that means that r's are getting smaller, 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 0, and then they become negative. And then at 3 pi over 2, I have a negative 2. So instead of going 2 units this way, I'm going to go 2 units that way. So this is giving me kind of a weird graph. And you can see that's why polar is so neat, is because you get graphs that look so much more interesting than the ones we've done so far in rectangular. So my r values are getting more and more negative as my angle is going from 7 pi over 6 down to 3 pi over 2. So they're getting further away in the opposite direction. So at 4 pi over 3, I'm getting a negative value. at, whatever this angle is, I'm getting a bigger negative value. 3 pi over 2, I'm getting the biggest negative r value. And then after 3 pi over 2, my r values are still negative, but getting less negative and eventually back to 0, somewhere between 11 pi over 6 and 2 pi. So let's finish this up. So we got another at 11 pi over 6 going a half unit the opposite direction. And then somewhere between 11 pi over 6 and 2 pi, I get 0. And then it slowly starts getting bigger, and at 2 pi, I get 1. So on this limacon, we wind up getting this inner loop as opposed to a bean that we got the last time. Okay, let's try one more. Once again, really try this. Hit pause, try it yourself, and then come back and see how you did. Okay, I'm going to do this one more quickly than the others. So on your mark, get set, go. It's a race. Just kidding. We're still dealing with the sine function. So I'm going to pick the same angles. Pi over 6 is a good one. Pi over 2, 5 pi over 6. Pi, everybody likes pi. 7 pi over 6. 3 pi over 2. That's the most negative sine will be. Then 11 pi over 6 and 2 pi. And let's figure out the r values. All right. I'm going to plug those angles in there. And we have to be a little careful here because we're doing 1 minus, and when we get negative values for sine, we're really going to be adding values instead of subtracting. So at 0, it's easy. The sine is 0, so 1 minus 0 is 0. On another planet, 1 minus 0 is 1. Let's try pi over 6. We're going to get a half. 2 times a half is 1. 1 minus 1 is 0. See, I was thinking ahead. Pi over 2. Now, what happens there? The sine is equal to 1 times 2 is 2. 1 minus 2 is negative 1. So once again, we're getting some negative r values that we're going to have to plot for certain angles. Let's go to the next one. That was 5 pi over 6. Well, I know that's the same as what's going to happen at pi over 6. So I'm going to get 0 again. How about at pi? Well, the sine of pi is 0, so I'm just going to get r equals 1. Now here's where it gets a little fun. At 7 pi over 6, the sine at 7 pi over 6 is negative 1/2 times 2 is negative 1, but it's 1 minus a negative 1, so that's 1 plus 1, which is 2. At 3 pi over 2, the sine is negative 1 times 2 is negative 2. 1 minus a negative 2 is going to give me a 3. So that's the biggest r values so far. At 11 pi over 6, I'm going to get 2 again, just like I did at 7 pi over 6. And at 2 pi, I should get the same as what I got at 0, so r is equal to 1. All right, so you see how this starts to go faster once you've done a few of them? So let's start plotting these. 0, 1, and then pi over 6. So by the time I get to pi over 6, I'm at 0. So that means that this graph r is getting smaller and smaller, and boom, it hits 0 by the time I get to pi over 6. And then at pi over 2, so let's see what's going on here. So at pi over 6, I got an r of 0. By the time I get to pi over 2, my r value is negative 1. So I'm getting negative r values between pi over 6 and pi over 2, which means my graphs are going to be going in the opposite, my points are going to be going in the opposite direction here. And the furthest it's going to go away in the opposite direction is at pi over 2, which gives me a negative 1. So I've got negative r's until I get to there. And then at 5 pi over 6, I'm going to get 0 again. So let me show this. So between pi over 2 and 5 pi over 6, once again, I'm getting negative r's. So my points are coming across on the other side here. And so my graph is going up this way. And then when I get to pi, r is equal to 1. So it's coming back like that. So now r is starting to get bigger. And it keeps getting bigger. At 7 pi over 6, I'm at 2. And at 3 pi over 2, I'm the biggest r value, and that is 3. At 11 pi over 6, I have 2 again. And then I'll be back. So r is getting bigger, 3, and then smaller, and back down to 1, and then we repeat. So we get another one of those inner loops on this graph. So that's the basics for graphing these limacons and most polar graphs in general. We make a table. But hopefully after doing a few more of these, we're going to see some patterns, and then we're going to be able to graph these a lot more quickly based on the patterns that we see, and we know what shapes they're going to take on.